problems using mathematical induction. So first I will connect the familiar statement of mathematical induction with the one we have studied in the last session. So usually we say that let P of n be a statement about n where n is a natural numbers. Suppose P of 1 is true and let k be a natural number. If P of k is true, then P of k plus 1 is true. Then we can say that P of n is true for all n element of natural numbers. This is our most familiar form of principle of mathematical induction. Now I will connect this one with our with the one we have stated in the last session. So I will I will define S as set of all n element of natural numbers for which P of n is true. I am defining S as set of all natural numbers for which P of n is true. Now here we have given that P of 1 is true. P of 1 is true means 1 is in S. If P of 1 is true, 1 is in S. Now the second statement, if P of k is true, then P of k plus 1 is true. So we have given that k is a natural number. If P of k is true, that means if if P of k is true, k is in S. If P of k is true, that means if k is in S, then P of k plus 1 is true, means k plus 1 element of S. Okay, then here we say that P of n is true for all n element of n. If P of n is true for all n element of n, then every natural number will be in S. That means S is equal to n. This is the statement we studied in last class. Okay, so both are same. Now I will move on to second version of principal mathematical induction. Second version of principal mathematical induction. The second version says that the only changes here we say that P of 1 is true. Okay, I will do one thing. Suppose my P of n is n square greater than 10. Okay, whether 1 square is greater than 10? No. So this statement is not true for n equal to 1. 2 square greater than 10, this is also false. So this statement is not true for n equal to 2. 3 square greater than 10, this is also false. So P of 3 is also not true. What about P of 4? 4 square greater than 10 is true. 5 square greater than 10 is true. From here onwards, we can say that n square is greater than 10. So I can say that this P of n is true for all n greater than or equal to 4. Can we use the idea of mathematical induction to do this? Of course. So as in the previous statement, assume that P of n is a statement about n element of natural numbers. Suppose P of n naught is true, and the second one is if or let k element of natural numbers and k greater than or equal to n naught. If P of k is true, then P of k plus 1 is true. These are the two conditions that should be satisfied. If P of k is true, then P of k plus 1 is true, where k is a natural number which is greater than or equal to n naught. Then the principle of mathematical induction second version says that P of n is true for all n element of natural numbers where n is greater than or equal to n naught. Okay, so this statement is known as principle of mathematical induction second version. That means here the statement regarding n is not true for all n element of natural numbers, but the first few natural numbers does not satisfy that statement, but all others will satisfy will make the statement true. In that case we can use the second version. Now one more result we have to study, principle of strong induction. Principle of strong induction. So the statement is here. There is only a small change. Let S subset of n S not equal to 5. That means S is a non-empty subset of natural numbers. Suppose S has the following two properties. S has following properties. Here the properties are, the first property is that 1 is in S, and the second statement says that let k be a natural number if 1, 2, etc. k is in S, then k plus 1 is in S. If this is true, then S is equal to n itself. So in the principle of mathematical induction, we say that if k is in S, then k plus 1 is in S. Here 1, 2, 3, etc. up to k, all these are in S, then k plus 1 is in S. The proof for this statement is same as proof for principle of mathematical induction. Okay, thus these are the theory part in this section. Now we have to prove problems on mathematical induction that I will discuss in the next session. Okay, all the best.